into this stuff, and it'll be a mix of lecture slides and then a couple hands-on exercises for everyone. So with that being said, let me start sharing my slides, and I'll do a bit more of an introduction and then an agenda sharing. All right, I'm assuming everyone can see my slides. If not, shout out. But this workshop is called Intro to Web App Security Testing. So we're going to cover web app security concepts, and then specifically I like to focus on like how to actually test for them manually. So you should all be able to learn and be more comfortable with identifying web app security vulnerabilities by the end of this. Like Tom said, my name is Ronnie. My handle on Twitter and blogging is Ropnop, and my personal email is right here. Feel free to reach out to me at any time if you want questions, advice, or anything like that. So, quick high-level agenda. I'm gonna do a brief introduction of myself, and then I'd like to get to know some of you, hopefully, and then we'll dive into just high-level security concepts. I think it's really important to start before we dive into technical security concepts to understand some of the vernacular and the language. I've been in the security industry for basically my entire career, and sometimes it can feel like we're talking a different language, especially when you're communicating like upwards to executives or downwards to engineers. So this is just kind of like to level set and get everyone on the same page when it comes to security concepts like threats and risks and vulnerabilities. Then we're going to go back to the basics, back to school for a little bit. I think, what is this, like week 10 for you all now within the cohort? Is that about right? Yeah. So I think at this point you've covered probably a lot of web application development, back end with Django, maybe some front end with like something like React. But before we get into like some of the technical vulnerability aspects, I want to make sure everyone's on the same page and we just go back to the very basics of what is HTTP, what is HTML, what is JavaScript, how do they all work together. So this might be a little bit of review, but it's a good opportunity to clean up or clear up any misconceptions or gaps you might have in your knowledge. Then we'll talk about some web vulnerabilities, specifically like the OWASP top 10. And then I'm going to do deep dives into 3 or 4 categories of vulnerabilities. We'll talk about cross-site scripting or XSS. We'll talk about cross-site request forgery or CSRF. We'll talk about injection attacks. And we will talk about cross-origin resource sharing or CORS, which is not a vulnerability. It's actually a feature, but it's oftentimes misconfigured or can be misconfigured, which leads to vulnerabilities. And then I'm hoping that these first 4 bullet points here are slide based. We'll have conversations around them. That should take us to maybe like a lunch break. And then after the lunch break, we'll come back and set up Burp Suite, which is a attack intercepting proxy for web application security. It's free, it's a community edition, so everyone will set that up. And then I've got a hands-on lab we can all walk through together. And then, as kind of a surprise or a little a fun exercise at the end, I set up, hopefully it all works out, a little CTF competition or a capture the flag competition, which is sponsored by OWASP. There'll be some challenges that everyone can walk through, a little bit of a scoreboard. You'll get points the more you complete, and we'll put a time limit on it, and whoever has the most points at the end wins a prize from OWASP. Awesome. So, like Tom said, my name is Ronnie. I work for a company called Marqeta. They're based in the Bay Area, but I'm actually based in downtown Chicago. I'm fairly new to Marqeta, just a couple months, but I joined there as a principal engineer on their product security group. So I'm working 100% at this point now with application security and working with developers to make sure that all of our web apps and our APIs are secure. Previously to Marqeta, I was the AppSec lead for Motorola Solutions and the AppSec lead for a company called Uptake, which is here in Chicago. And then before that, I really spent the majority of my career as a consultant and a penetration tester. So I got started in security on the offensive side of things. I was a red teamer, I was a breaker with NeoHapsys, and then with Cisco. Companies paid us to hack into their networks or find weaknesses and vulnerabilities in their web apps or their mobile apps or whatever it was they were selling. And we would just wreak havoc. And then we would just write reports and give recommendations on how to fix it. And after doing that for several years, I learned a lot. I definitely learned a ton of different technologies. We got pretty good at it, but it kind of became the same thing over and over again. And I realized that I wanted to switch and actually start defending against these types of attacks, and working more closely with developers and engineers. And so I got out of the offensive side, although I still have a soft spot. My passion's still there. I still do a lot of like research and open source tooling on the offensive side of security, but professionally, I'm more on the defensive side now. So you can follow me on Twitter or GitHub. I've got some open source tools, and actually one of the labs are open source, and on my GitHub as well. And I blog occasionally. And my email, I guess I was on the first slide, so feel free to reach out. So I wanted to pause there, and I would actually love to get to know you all. I didn't realize how big the cohort was, so it might be too big to go like one by one and actually introduce yourself. But if anyone wants to speak out and introduce themselves, I'd love to hear how the class and is going, what you've been learning, what you're interested in, and if you have any background or experience in security, or if not, that's fine. What is there anything specifically, web app security or security in general that you're interested in learning about? Don't all go at once. Maybe I'll ask a question. Is anyone working, or have worked for a company and interacted with a security team or a security engineer before? And how was the experience? Anything?
I have, Ronnie. I was doing signals intelligence in the Marines, and then I went on to do some contracting at NSA, also doing signals intelligence. But
Very
it's a
cool.
little bit different than cybersecurity because signals intelligence is interested in things that are more than just IP based. But my ultimate goal is to try to get into or break into security engineering. So
Awesome.
yeah.
Cool. Yeah, great to hear. Then hopefully this will help you out. And yeah, if I can help out in any way, or you have questions or want advice or anything, just let me know. Uh, Anyone else have a desire to maybe get into cybersecurity or take this path of, I know you're learning web development, but there's definitely a huge overlap between like web development and web security or cybersecurity.
Yeah, as far as I know, like just being a software engineer isn't enough. You also have to understand all the security that's going on behind the scenes, and to ensure that you have a secure app. So everyone's responsible for securing their own code, essentially. So if you don't know anything about it, um, when you join your teams, if you know a decent amount about it, you'll be definitely an asset.
100%. Yeah, 1000%. Couldn't agree more with that. And yeah, I will mention that. And in today's day and age, if you want to be an engineer of any kind, you have to know a little bit of cybersecurity. They're just becoming so intertwined, that having cybersecurity knowledge, even if it's not your primary passion or goal or objective in your career, having cybersecurity knowledge is still going to propel you and make you better at whatever it is you want to do. Cool. Who's heard of OWASP before? See a few people maybe raising hands. So I'm actually here on behalf or representing OWASP, and OWASP stands for the Open Web Application Security Project. It's a nonprofit organization that is worldwide, with chapters in almost every major city or major metro area. And it is a great organization that does, in my opinion, a lot of good for the cybersecurity world. It's basically made up of a lot of security engineers, developers, practitioners, and we put out just a lot of free resources, tools, and trainings to help people be more secure when they do web development. It's 100% focused on web security. It's 100% free open source materials. And like I said, we're a nonprofit, and we have chapters in most major areas. I'm heavily involved in the Chicago chapter. No matter where you are in the world, you could probably find an OWASP chapter. 2020 has been a little bit weird, so we haven't actually met in 2020, but usually like the Chicago chapter, we get together once a month or once a quarter and give free trainings or free presentations, or it's just a great networking event to join. So OWASP puts out a lot of material, but probably the biggest or most popular material is the OWASP Top 10, which we'll definitely talk about in a little bit, which is a list that we release every 4 years of the top 10 web application security risks based on a culmination of data, self-reported from industries or what we've seen in the wild. Like, these are the top 10 risks you need to be aware of. The ASVS is the Application Security Verification Standard. It's a checklist if you're developing an application of standards of things to look for security. Great resource for organizations. SAM is the Security Assurance Maturity Model. It's more of a controls framework for organizations that want to build security programs. And OWASP ZAP, or the Z Attack Proxy, is a free open source tool that will do manual penetration testing or automated scanning of web applications. There's also conferences. There's usually, it'd be happening, it would have happened about last month, but was canceled, a global meetup of OWASP in various cities around the world with talks and trainings, and all this stuff ends up free online. So if you haven't heard of them, now you have. OWASP is a great organization and tons of really good resources out there. Okay, so with that out of the way, I will kind of now dive into what I talked about earlier, which is those high-level security concepts. And some of you raised your hand that you've worked with security team before, so you may be familiar with a couple of these concepts, but it's good to review. So this is what Tom was saying just a minute ago. Jim Manico is one of the OWASP board members, or former board member. Great guy, great trainer. And he put this tweet out there that I could not agree with more. It says, "From my experience, all software developers are now security engineers, whether they know it, admit to it, or do it. Your code is now the security of the org you work for." And I really think that sums it up kind of nicely. Like Tom mentioned, if you are developing code for an organization, you have to know security. You are the frontline defense on the cybersecurity field, whether you know it or not, and whether you actually think you're doing it or not. Like, really, you are. And so in today's day and age, security is no longer a specialized silo. The traditional security team that sits by themselves and has all the specialized knowledge is really falling apart and breaking apart. Everyone's job is security. And everyone needs to know a little bit of security because they're doing it on a daily basis, whether they know it or not. There's also been this massive shift towards DevOps. Huge buzzword. I'm sure you've talked or heard about DevOps and what that means. Has a lot of different definitions and meanings. But one of the main things that it brought about is this concept of total ownership of code. It means no longer, as we're developing code, are we only responsible for the code itself. We're responsible end to end for the entire product, or the entire deployment or operations of our code and our product. And that also means owning your security. And then from my perspective, because I've been on and run application security teams, we are no longer becoming the gatekeepers. We can't just be the gatekeepers who are standing there and telling you go, no go. Like, yes, you can deploy, no, you can't deploy. Yes, you're secure, no, you're not secure. Application security's job has morphed to be more of like an enabler. How can we help you be more secure, and how can we help you develop more rapidly while still shipping secure code? So to summarize, really, to be a successful developer in today's age, and I know a lot of you are going to be starting your careers in web application development or some sort of software engineering, you'll have to know security concepts. And the more you know and the more you do, the better of developer you will actually be, or the more valuable developer to your organization. So that's why I'm actually super happy when Code Platoon reached out to even ask if we were interested in teaching a course like this. It's like, yes, this is exactly the type of material and the stuff that I'd love to cover for people who may be beginning their careers in software engineering or learning how to do web development. All right, this is the lingo that I was talking about, right? When we are in the security field, we throw around a lot of terms. When we're talking with executives or legal counsel, we're throwing around terms like this. And a lot of this actually stems from the government, from some initial documentation from like the Department of Defense or NIST. But these are important terms to know as we talk about security, and it's really good to be able to know these terms and speak the language. Expressing, some deep technical ideas in these types of terminology goes a long way, especially if you're talking upwards to like a CEO or a CTO who may not know the ins and outs of code. They understand terms like this. So on the left here, anyone heard of this before or seen the CIA triad before? They call it like the golden triangle or the golden triad of security. Confidentiality, integrity, and availability. Almost everything in security engineering, we're trying to improve all of these. Confidentiality of data, integrity of data, or confidentiality of systems, integrity of systems or data, and the availability. But like any sort of three-way triangle, if you improve one, you're probably going to lose the other. You can't always have all of them be 100%. There's an old joke or an adage in security industry that the most secure system out there is one that's powered off. But that makes your availability go down to 0. But yeah, your confidentiality and your integrity are going to be the best you can possibly have. So it's also really important to think about when you're developing your web app or working for your organization, like which one of these are more important? Which ones are more important? Currently at Marqeta, like I work in the fintech space or the financial tech space. So confidentiality and integrity are extremely important to us. Integrity especially so with the amounts of money that we're dealing with and the ledgers that we have to maintain. The integrity of our data and making sure that it hasn't been tampered with is paramount. Now, previous to Marqeta, I was at Motorola Solutions, and we made the software and the hardware that powered like 911 call centers and the communications grids for first responders. Availability was by far the most important there. Every decision we made, we had to make sure the system would never go down because lives were at stake, literally, with the systems that we were designing. So it depends in the organization of the context, right? Like which one of these is the more important, because there's always going to be trade-offs. Now on the right here is another table of terms, and you'll hear me and a lot of people throw around the term vulnerability a lot. But vulnerabilities don't exist in a bubble. Really the main things that we need to always think about is vulnerabilities have to be exploited by something. And vulnerabilities can always be patched by something. And when vulnerabilities are exploited, they introduce risk. And when vulnerabilities are patched, they reduce risk. But who exploits a vulnerability? Threat actors, which are usually people or teams or nation states, and they leverage threats, which exploits vulnerabilities. When we patch, if we fix our code because we identified a vulnerability, sometimes we call that a control. So if you hear that term too, like what controls are in place or we introduced controls, it means we've either fixed the vulnerability, we patched the vulnerability, or we built something else around it that reduced the risk. The other thing to just mention is threats always exist. Threats just exist in the world. We can identify all the threats. There's really not a lot we can do about threats. They're just there. But threats need a vulnerability in order to actually pose risk to an organization. So you could have all the threats in the world, but as long as you have better controls the threats, you're not going to have much risk. By the way, I can't, somehow I lost the video of you all, but if you have any questions, just unmute and shout it out because I can't see if anyone is raising their hand or nodding along or not. Yeah, I don't know what happened. Oh well. So it's always important to think like an attacker. And I know I'm speaking of this because in my background, I started off as an attack simulator, like a red teamer. But we have to understand the threats and the vulnerabilities, and combined, we understand risk. And we can find threats and vulnerabilities through things like threat modeling or vulnerability scanning or testing, which we'll get to in the next couple slides. So I'd like to pause here and kind of do a little exercise, because I think it's really useful to take these definitions and these terms and apply them not to abstract context or abstract concepts like technology or code, but to real world systems. So let's say that all of us are in charge of building and designing a new bank. And it's like an old-fashioned bank, like in the Wild West, where we actually are keeping a bunch of money and gold in the vault. We are in charge of the security of that bank. So we have to think of these things to actually design the most secure bank we possibly can. So I'll pose the question and unmute yourself and just shout it out. Like starting with threats, what are some of the threats to a bank? If we're in charge of the security of a bank, like what threats do we need to be aware of? And who are the threat actors that might be carrying out those threats?
Robbery at gunpoint.
Yeah, perfect. Yep, definitely. So just strong-armed robbery, or just bank robbery in general, right? Someone coming in to steal the gold or steal the cash. That's definitely the threat. That might be the biggest threat for a bank. And in that case, who would the threat actors be? It'd be just bad guys, right? The robbers, bank robbers, Bonnie and Clyde. Anyone else think of any other threats to a bank? Something else besides robbery?
Employees stealing from the bank.
Okay, yeah, that's a good one. So insider threats, for sure, that's huge, especially in like a lot of orgs today. Insider threats are giant. So the threat actors there could be your own employees, and the threats could be embezzlement, or would you consider just an employee fat fingering a number as they're typing in a withdrawal slip to be a threat?
Yep.
Definitely. Yep. And then in that case, the threat actor there isn't necessarily a malicious insider. It's just, someone who is bad at typing and made a typo. So not all threats and threat actors are necessarily malicious intent, but we got to think about these things. Anyone else?
What about running out of money or just running out of resources in general?
Yeah. Yep. That's another good one. So yeah, threats don't all have to be doom and gloom or like we're under attack, right? There's very existential threats to a bank, which is we've lent out more money than we actually have, and now we're bankrupt. That would definitely be a threat, or losing the ledger or something like that. There's for sure financial risk involved in a bank, not just technical risk.
Identity issues.
What do you mean by that?
Like, I guess it sort of is like robbery, but like people posing as account holders when they're not, or
Oh yeah.
people hiding what they do with them, with funding terrorist groups, or something like that money laundering, that kind of thing.
Yeah, great point. I think that's really important to actually distinguish between someone just coming in with a gun saying, give me your money, and someone coming in with a fake ID and saying, give me, so-and-so's money. That's definitely a threat. And those imposters, those con artists might be the threat actors there. Yeah, these are good. So I think we just,
users.
I'm sorry, go ahead.
I'm sorry, the user.
You broke up a little bit there. What was that?
Oh, the users. They could also like put out their information and not be aware of things. And
yeah, they might get phished, right? Or they might get social engineered and lose their data. The end users are definitely threats, and in both regards, right? The end users could be malicious, like someone who's a member of the bank trying deliberately to hack it, but more likely just an average user who makes a mistake, clicks the wrong button, gives the information to someone he shouldn't have. Just kind of like the malicious insider, or the insider. They don't always have to be malicious. They could just be, making a mistake.
In general, I think related to what Augie said, basically like fraud, like if someone's passing a bad check or just trying to take advantage of the bank in those means.
Yep. Yeah, definitely. So I think we just enumerated some really good threats and definitely talked about threat actors. So the next level here, kind of building on what we've all just talked about, right? What are vulnerabilities? What are the possible vulnerabilities? So to help you understand, right, threats exist in a bubble. Like threats always exist. So the bank robbery crew with their machine guns are threats. They're threat actors. The threat is armed robbery, but that armed robbery is not going to be successful unless there is potential vulnerabilities. So what would potential vulnerabilities look like that would make armed robbery much more likely in our bank?
Not having a vault.
Mm-hmm.
Lack of security controls.
Out of date software, out of date infrastructure,
Yeah.
risky people.
Yep.
Maybe not having a security guard on staff.
Yeah. Yep. Those are all really good. Definitely, there's a lot we could do to make armed robbery much more likely. There's a lot we could do or not do to make fraud or impersonation much more likely. And circling back to I forget who it was that mentioned, or we were talking about just like an insider, and it may not be a malicious insider. It might just be someone who fat fingered an extra zero on like a withdrawal slip. Well, that shouldn't be an issue unless we don't have a proper system to like detect or prevent that. So the lack of something like that could also be a vulnerability, or the lack of security awareness training to our users who are falling for phishing links or clicking on things could be vulnerabilities. And then finally, so based on the vulnerabilities, what are quote unquote controls that we would put into place to mitigate or limit the vulnerabilities, and then by proxy limit or eliminate the threats?
A good user interface.
Yeah, that's actually so undervalued. That's a great point. Like having just good user, like clear user experience and user interface, like minimizes the chance of mistakes, right?
Public key infrastructure.
Okay, yeah. I love a good crypto system for sure. Yeah, so we could have strong cryptography to make sure stuff's encrypted and not tampered with. It's really the inverse of some of the vulns that we were just saying, like someone mentioned not having a vault. I mean, having a strong, good vault is a big control. Having the armed guard staffed 24/7 is a control. Having security cameras or auto locking doors, these are controls. These are things that we're putting into place to limit those vulnerabilities from being exploited by the threats. So that was really good. Great like brainstorming session. So what we just did there is a threat model, and this is basically what you would do exactly for a web application or a technical system as well. You start with identifying threats and threat actors. You go through vulnerabilities. You think about controls, and then you figure out what work you need to do, or if you don't have something, what your gaps are. So everything we just talked about for a bank, take that mindset the next time you're developing a web application and think about the same way. What could happen here? What could I put here to make sure that doesn't happen? Who could be attacking me, or what would they want from my bank? What would they want from my web app? So yeah, that was great. You guys did a really good job there. So we just talked about what we did is called threat modeling. That's one technique to find and identify vulnerabilities in like a web application or a system. In most mature security organizations, it's going to be one of many. There's a lot of different techniques we can use to identify vulnerabilities in our code. So threat modeling is high level, usually involves just a meeting and a whiteboard and brainstorming like we did. But the next are a bit more technical. So you'll hear me throw around the term, or you hear people throw around the term static code testing or static analysis or SAST. This is like regex for your code, where we're actually looking at your source code, or think of it like spell check for your code. There's tools out there that can just read the source code that you write and tell you or identify if there's vulnerability or weaknesses inside there. There's also dynamic application security testing, or DAST. DAST is separate than SAST because your code actually starts running. And instead of looking at your code, DAST is looking at what the running application is actually doing. And so in the web world, that's actively probing and scanning and sending HTTP requests to your server to identify unexpected behavior or vulnerabilities. Software composition analysis, or SCA, involves looking at your open source components. The world is open source. There's some crazy stats and studies that have come out that in large enterprise software, upwards of 80% of the code inside there is open source. I've seen some studies that say like 90 to 95% of the code in most software is open source at this point. So really, as we're developers, we're only writing the smallest fraction of the code at the very top, but we have this huge iceberg underneath the ocean of code that someone else wrote. And we don't know if that's secure or not. There might be vulnerabilities in there. That's what software composition analysis does, identify the open source components and find vulnerabilities inside there. Then we have penetration testing. This is our focus today, and it's a manual test to validate controls and identify vulnerabilities. In our bank example, a penetration test would be akin to actually saying, like, paying someone to come in after hours and try to break into the vault and tell us if you can or not. And that's kind of what pen testing is for an application. And then lastly, vulnerability scanning is more of an automated form of penetration testing in which you're looking for the vulnerabilities in the network or infrastructure components, including containers that are running the applications. Now, I've said the word pen test a bunch already, and unfortunately, that is a very overloaded term. And coming from the consulting background, we talked with clients constantly that would ask for a pen test, but didn't really know what they were asking for. So pen test can actually mean a lot of different things. And an old coworker of mine put this chart together that I think is a great kind of visual explanation of what we're trying to accomplish when we do a pen test. The two axes are the scope and the details given to the testers. So scope meaning, how targeted is this? Or a full scope might be like, we're going to target the entire company, any avenue we can possibly find. Whereas a really small scope might be like, we're just going to look at this one API endpoint. And then the details given to the tester, we'll call that sometimes black box or white box. In a black box pen test, the pen tester has no knowledge at all. It's just whatever you can find to see if you can get in. But in a full white box, here's the source code, here's the documentation, here's everything. You have all the knowledge. So all these factors come into play when we're just trying to figure out, what are we trying to accomplish here, whether it's for compliance purposes, attacker simulation, or just general overall risk reduction. If we're testing our own code, it's somewhere a mix over here, right? Depending on the scope of what we're trying to accomplish, but we know our own source code, we have our own tools, and we'll find that. Make sense?
So what does it cost a client more? I imagine a larger scope costs more, but what does does it cost more to have somebody come to a white box where they can see everything, or a black box where they can't see everything?
Yeah, good question. That usually doesn't factor too much into it. If you're hiring a consultant, they're going to charge by the hour. So really what you do is you sit down with them, or they would sit down with you and try to figure out how many hours we're going to need to accurately do what you want. And that's ultimately what's going to drive the price. So you have a lot of levers to pull depending on how many hours you think it would take. The big one would just be the scope, right? The smaller the scope, like the less you're going to focus on, the shorter it can be the shorter time frame it can be accomplished in, the cheaper it's going to be. So yeah, full scope, like we had done some in the past of like an entire organization is in scope for a red team assessment, and it was going to take 6 to 9 months to do. Like it was a huge project. Whereas sometimes it'll be like, hey, we have a new API we need you to test. It's just like 1 or 2 endpoints. Like, okay, that'll be 3 to 5 days. Now, when it comes to white box versus black box, white box testing usually can go quicker because you don't have that ramp up period. Like the first couple steps of a pen test, if you're coming at it from a black box approach, is trying to find out information, trying to figure out how the app works, like what it does, who the users are. And so that can take a couple days, couple days to weeks, depending on the scope. So if you give all the information up front, which is what I would always try to ask for if I was doing a pen test, like in cooperation, the more information you give me, the quicker we can get this done. Because I'll find it out eventually, but you're just going to save me the time by letting me know the innards of the app. Does that answer your question?
It does. Thank you.
All right. So before we go on, quick disclaimer here, right? With great power comes great responsibility. As we start talking about pen testing and we start using tools or explaining like how web vulnerabilities work, I really just want to stress that you can only do this against things you have permission to actually do it against. And so that's, we're going to learn, or you're going to see, what attackers look for and how to test and find and exploit specific vulnerabilities. But you can't just do this against any application. You can't do this against your internal company's application unless you have the permission to do it. Like this stuff could cause harm, could bring systems down, could have adverse effects. Important to know. And the great thing is there's actually so many free resources out there that give you plenty of permission to do this that it's not hard to find things to practice against. There's really good like free vulnerable web apps that are just open source online that you can download and run locally or deploy in your own lab. Or if you're inclined, companies that have bug bounty programs are essentially giving you permission. If you look at the rules and what's in scope for a bug bounty program, they will say, go ahead and feel free to hit these apps or these URLs as much as you want. And that's a great opportunity to actually try and find vulnerabilities or just practice your technique with companies that are giving you explicit permission to. All right, how are we doing on time? Good. We'll blow through this and then we'll take a coffee break or something when we finish the Web 101 stuff. Bear with me 1 second since I lost my camera or video on my Zoom, so I'm just going to stop sharing for a second. Oh well, I can't figure it out. I used to be able to see like your faces on the side and it's not there anymore. So if you're waving your hand or nodding your head or something, I can't see it. So just unmute, like I said, and ask your question. All right, time to go back to school, back to the basics here. Apologies in advance if some of this is like so basic and you learned this week 1 of your cohort or you know this already, but you would actually be surprised the amount of times I've given this training, especially to like security engineers, like actual pen testers who didn't understand some of these concepts. So I'm going back to the basics and we're just gonna start from scratch and build upon this because it's really important to know the underlying principles of these technologies and why these attacks work than just learning the attacks themselves. So that's one of my pet peeves with a lot of bug bounty training or pen test training out there is they immediately jump into the vulnerabilities. They say, hey, here's the exact attack and here's how it works, or here's how to exploit it. But they don't really go into like why it works in the first place. And if you can understand why an attack works, then you can understand why and how to fix it. So if you don't understand those core underlying issues, then fixing security bugs in web apps is like playing whack-a-mole. And if you have a bug bounty program or you're hiring out pen testers, there's nothing more frustrating than just seeing the same vulnerabilities keep popping up time and time and time again because they're not fixing the core underlying issue that's causing those. So even really experienced developers and pen testers mix up things like cores and CSRF and XSS. And that's what we're going to be talking about in this training, and by going back to basics and building upon that so that we can understand why these attacks work so we can learn how to defend against them. All right, here we go. Back to basics here. Web technologies, what powers the World Wide Web? Want to call out the distinction between some of these terms or these languages. Starting with HTTP. HTTP is the protocol. A protocol is just a definition or a contract on how data is going to be interchanged between two entities. So HTTP is not a language, it just describes how data gets sent between two things. And it's a very well-defined protocol with accepted verbs and headers, and it's plain text. That's important for us because it means it's really easy to read and parse HTTP traffic and understand what's going on. Now, HTTP is generally over TCP, which is the networking protocol, over ports 80 and 443. 80 is for plain text HTTP, and 443 is for HTTPS, which is HTTP wrapped around TLS or SSL. But even when it's encrypted with HTTPS, the protocol isn't actually, the verbs or the words underneath, aren't actually any different. If you can decrypt it, it's the same thing as plain text HTTP. HTML is a markup language that describes to the browser how to render a page. So one important thing just to clarify is HTML is not a programming language. It's not a feature complete. You can't just write a program in HTML. There's not enough logic within HTML to do that. All HTML is what they call a markup language. It's a description language. It describes the data that it's carrying in a format. And it's not unlike XML or JSON. It's just a way to put data in a format that something can understand. And in most cases, that something is the browser. So HTML is giving the browser and saying, here's all the data, make this a pretty page. CSS is style metadata associated with the HTML. It can either be inside the HTML or as a separate CSS page, but all it does is it just describes like how to render the HTML, how to make it look, what colors, what size, animations, transitions, nav bars. A lot of that gets put into CSS and then gets sent alongside with the HTML. So HTML and CSS get packaged up. They get sent over HTTP, which is the protocol. A browser like Firefox receives all of that over HTTP, unpacks it, reads the HTML, reads the CSS, merges them together, and builds what's called a document object model, or a DOM. Have any of you heard of the DOM before? If you're doing like front-end client-side applications or programming, like the DOM is a really important concept in JavaScript.
Yes,
Yeah, we've heard of that.
Definitely gone
Awesome.
over that.
Cool. So yeah, the DOM is ultimately, you can kind of think of it as like what gets displayed and clicked on by the end user. So here in our example site, Firefox takes the HTML, the CSS, constructs a DOM, and we start interacting with it. There's one glaring omission here from the web technologies, and that's JavaScript. So in the world of web, JavaScript is king, and it's just eating everything else. JavaScript is powering everything now. And as opposed to HTML, JavaScript is a complete programming language. You can do anything in JavaScript. There's enough logic and enough power in JavaScript to pretty much do whatever you want. Now, JavaScript can be on the server side or the client side inside the browser. Since JavaScript it's a full language, it's like C or C++ or Python. But because JavaScript is so powerful, browsers have their own JavaScript engine that executes the loaded code, and they execute it and load it inside a sandbox. So the JavaScript engine that's inside Chrome or the JavaScript engine that's inside Firefox is not the same JavaScript engine that's inside Node.js that runs on your server. They're very similar, but it's missing some core features and doesn't have the same powerful access that Node.js does when you're executing JavaScript inside your browser. And that's by security design, as well as just some limitations of what browsers can do. When JavaScript is executing inside your browser, it has full read and write control of the DOM. And that's exactly how frameworks like React work. They construct the DOM and they modify the DOM and they play with the DOM and they build everything you see, the entire UI, via JavaScript by modifying the DOM. JavaScript also has full access via browser APIs to things like storage within your browser, things like cookies within your browser, and a lot of other browser APIs. There's more and more that are added. I'm talking to you now. I guess this is Zoom, so it's not a browser, but a JavaScript can talk to your webcam. It can talk to your microphone. It can talk to USB storage via browser APIs. More and more features get added, so JavaScript can start doing a lot more things than just rendering the DOM. It can build really cool, really awesome, high-tech web applications nowadays. But like I mentioned, it's very important to recognize that when you're executing JavaScript, you're in the browser, you're executing it inside a sandbox, and we rely heavily on the browser. I wanted to say manufacturers, but that sounds like they're made in a factory. The browser developers, whether it's Mozilla or Google or Microsoft, to make sure their browser JavaScript engine and their browser JavaScript sandbox is secure. And for the most part, it is. Exploits and bypasses of JavaScript sandboxes within browsers are rare. When they happen, they're big deals and they're patched very, very quickly.
Ronnie,
Yep.
do you think it's good or bad or doesn't matter for security that a single language is that people are it's like developing a critical mass kind of and sucking people in? Is it good to have lots of different languages that people are working in, or is it better to have just one?
Oh, good question. I would say, for the most part, I'm actually pretty happy with the ubiquity of JavaScript. And I actually like that JavaScript is becoming a language. So before JavaScript, like Node.js got super popular, there was clear delineation between like back end and front end. Like JavaScript was always on the front end, but on the back end you had Java, or you had Ruby, or Ruby on Rails, or Python. But what that led to was developers specializing in different areas, where I'm purely a back-end developer or I'm purely a front-end developer. I think by having one common language across both of them, it's opened the door to developers becoming quote unquote full stack developers more easily and understanding both, which I think can only improve security, because you no longer have this game of just like the two sides of the house pointing at each other and saying that's a back-end issue, no, it's a front-end issue. Like now they can work together and solve the same common issue.
Thanks.
Yep. Now, others in the industry might disagree with me. Some people joke that like JavaScript is a security nightmare. There's definitely some issues with JavaScript, especially around the ecosystem. Remember I talked about how much open source is out there? I mean, there's so much open source random JavaScript in NPM. And when you're doing an NPM install and pulling in a package, like you don't necessarily know if the author of that package is writing secure JavaScript, but now you're running it in production. That's a little terrifying, but that comes with any language and any open source. Actually, I think I had this open for a different demo I was giving, but if you do, I always like to do this, right? Just do a create React app on an empty directory. So just the basic boilerplate React hello world, and then count the files and lines of code that actually get created in that directory before you've even written a single line of code yourself. I think last time I did this, it was up to like 1.7 million lines of JavaScript get downloaded onto your laptop just to spin up that initial React Hello World site. So you're downloading a 1.7 million lines of code that may or may not have security implications. Little scary when you think about it, but that's just the way the world is now. Yeah, good question. Okay, so going back to HTTP, if you haven't seen it before, this is HTTP. It's plain text, and everything is in ASCII words. Makes it very easy to parse and read and even write yourself if you'd like. So this right here is my terminal, opening a TCP connection on port 80 to www.google.com. So I'm talking to one of Google's servers, and I can just write some plain words, get slash, so get is the verb, slash is the path, HTTP 1.0 is the version I want to use. And Google understands that single line and dumps back HTTP to me. The HTTP response that comes back is always divided up into two sections. You've got headers and the body, and they're separated by a new line character. The headers are basically information that the browser will understand. And so there's a lot of custom headers in here that my browser is just going to take care of and understand things for me, including cookies. And then the body is always going to be, well, not always, but generally going to be like HTML or something that the browser is going to render for me. So then my HTML starts, and this is what the browser starts rendering and building the DOM from. One really important note about HTTP is HTTP is a stateless protocol. And what that means, as opposed to a stateful protocol, is that every single HTTP request to the server and the response that comes back is standalone, and the connection is closed when it's done. So the server never remembers who it's actually talking to. It doesn't keep up like a constant stateful connection between me and the server and knows that it's always talking to Ronnie. Every single HTTP request that the server sends is like a brand new request to that server, and it has to remember somehow on its own who's actually sending it. So that means that every single HTTP request has to include its own identifying information, which is where cookies come in. So since HTTP is a plain text protocol, certain characters have to be encoded. So remember I said like this new line character right here between the headers and the body is super important. That's actually what distinguishes the header and the body. So you can't actually have a new line character anywhere else in your HTTP headers because the browser or the client will think that's an actual break between the header and the body. So things like new line characters have very special meaning, so you can't just send them as is. And that's where encoding comes in. I'd be remiss to not remind everyone that encoding does not equal encrypting. When we encode something, we're changing the format of the data, but there's no security at all that we're getting from that change of format. This is literally just masking or changing data from one format to another. And web apps use various types of encoding all the time. And as you start peeking under the hood of HTTP and doing testing yourself, it's really useful to be able to kind of just spot them by eye and know what kind of encoding there is. So these are 4 different encoding schemes. All of this string hello world with an exclamation mark. You've got URL encoding, HTML encoding, ASCII hex, and base 64. Oftentimes in HTTP, the plain ASCII letters and numbers will not be encoded, but the special characters will. So this is more likely what you'd see. Hello, the space gets replaced with a plus, and the exclamation point gets replaced with %21. So I mentioned that HTTP is stateless, and this is really a core concept in web security. I don't want to say it was a mistake because this was invented, I think, even before I was born. But it is what it is, and everything since then has kind of been like a bolted-on hack to HTTP to try to manage state. And they do that by introducing cookies. So cookies were not actually initially part of the HTTP spec. They were added on later because they needed to solve this problem, where a server is not going to remember who it's talking to, and if you didn't have cookies, you'd have no way of doing like any sort of session management or authentication. So browsers send and receive cookies in HTTP headers, and then browsers store and remember all those cookies in what's called a cookie jar, which is organized by domain. And we'll see that there's some security issues that can come from cookies, and there's a couple things you can do to make cookies more secure. Quick question, I guess, for the group, since I think your backend servers are using Django, are you using cookies for session management with the Django framework?
No. We're not actually using cookies with session management. Yesterday we actually just used JavaScript Web Token.
Nice. That's definitely the newer, in my opinion, better way of doing things, but it's still very common to see web applications using cookies for session management. So cookies are usually an identifier, like a random string or an encrypted string. It's used to correlate the client state with server side. So you can kind of think of cookies as like when you go into a nightclub or go into Disneyland, you get like a stamp or a wristband. And then you can come and go, and as long as you have that stamp or that wristband, they know who you are. That's kind of what happens when you visit a site and you log in. The server gives your browser a wristband or a stamp, which is a cookie, and then any subsequent request you want to send to the server, your browser is going to send that cookie with every request and identify yourself to the server. The problem is that browsers are extremely helpful and will send cookies automatically without asking you. And this has some security implications. It definitely also has some privacy implications. Things like tracking cookies got out of control, where cookies were being used to identify you on sites where you maybe didn't want to be identified or didn't even know that you could be identified. Tracking cookies and advertising cookies are everywhere, very prevalent. So there's also other uses for cookies besides what they were initially designed for. And cookies over the years have also had some flags added to improve the security of them. HTTP only means do not let JavaScript read or write the values. Super important. We'll talk about when we get to cross-site scripting. Secure means don't send them over plain text HTTP. And same site, which I'm not sure if how many of you have heard of this, because this is actually a really cool new exciting feature that came, I think it's in the newest versions of like Chrome supported now, but not every site supports it. That basically stops things like advertising and tracking cookies from being sent without being explicitly allowed by the user or the server. So besides cookies, browsers also have storage APIs that can be leveraged by JavaScript to store information. So cookies are one way of storing information within the browser, but the more modern approach is not using cookies and using either local storage or session storage.
Jeremy, I have a question about the previous.
Oh, sure. I'm sorry. Yep.
The same site thing, is that like when you go to a website and it asks you, do you accept cookies from this website? Is that what that is?
No, that's I think mostly like GDPR. That came out of a lot of the privacy regulations around storing personal information, and they consider like tracking IPs as personal information. So that came from compliance and legal requirements, which is a good thing. Same site actually, for the average end user, you wouldn't even know what's happening. But what same site does is if here's an example, you know the site medium.com, blogging, or people post their blogs on Medium. If you've ever gone to Medium, and I don't even have an account on Medium, but I'll go to Medium and immediately in like the top right, it'll pop up and be like, do you want to log in? Hi Ronnie, do you want to log in with your Google account, rflathers@gmail.com? How does Medium know that I'm rflathers@gmail.com? It's because I have a cookie for Gmail, and Medium in the background sent a request to Google, and my browser automatically sent my cookie. With same site, that's no longer allowed. I can't be on Medium and send a cookie to Google because they're different sites. I can only send cookies to Google if I'm on Google. Does that make sense?
I think so. Thank you.
So how does the browser, like if you're on a Chrome browser,
Mhm.
Does that count as being on Google on every single site you're on? Like how do they distinguish the browser from the site if it's made by one company that does both things?
So there's a technical answer, and then there's like the conspiracy answer. The conspiracy answer is like Google definitely is probably blending some of that. Like, yeah, like what happens when Chrome and Google owns the world and everything is touching Google? Like, where does the privacy delineation happen? But from the technical answer, cookies are always stored and organized by domain. So when I log into Gmail, Google is sending me a cookie. The browser is putting that into secure cookie jar and marking it as only for google.com or star.google.com. When I'm on medium.com, my browser knows that I'm on medium.com. That's the origin that gets set for that DOM. So if a request is being made in the background to Google from Medium, the browser will know that the origin is different, and with the same site flag, will not reach into the cookie jar and pull out google.com's cookies unless the origin or the parent page is also Google.
And is the same site something that I can turn on my browser, or something that a site would have to choose to build into it? Because obviously Medium wants to be getting as much information about me as possible from Google, and they're never going to add that to their site, right?
Yeah, so this is a push from the browser community to turn this on, and they've actually delayed turning it on multiple times because of how much it's going to break. Like sites like Medium, who don't want this to happen. It's something that you have to opt in as a server. So Google opts in by setting the same site flag on all their cookies and saying, I don't want this cookie to ever be sent from any other site except my own. And then the new browsers will honor that. But I don't know exactly where the support lands. The default is to be lax with those requirements. So if like same site is not set, they kind of ignore the flag. The big thing that same site prevents is CSRF. So when we talk about CSRF, we'll circle back and I'll try to explain this a little bit better. Without diagrams, I know it's like hard to visualize, but we'll definitely talk a little bit more about that later. As a web developer, though, if you are building a new application server that's using cookies, add the same site flag. It's the best you can do. Whether or not every browser out there supports it, whether or not they honor it yet, you can future-proof your application and build it more security by putting the same site flag there. Yeah, great questions. So with switching gears slightly, still talking about browser storage, besides cookies, there's two other ways that browsers can store information and an app can store information inside the browser. And the main ones are local storage and session storage. And the distinction between these two is that local storage is persistent. And if you close your browser and then reopen it, it stays there. Whereas session storage is ephemeral. So if you close your browser, you lose your session storage. But these are basically, you can think of them as like mini databases inside your browser that JavaScript can read and write to. It's pretty cool, and you can put a lot of stuff in there. It's not just for session cookies. Sites use this to build caches or store a bunch of information locally that they don't want to constantly be fetching from the server. They'll just fill up your local storage or your session storage in your browser and make things like appear much snappier or faster. And one thing to note is JavaScript cannot always access your cookies. If HTTP only cookies are set, JavaScript cannot read or write to cookies, but browser storage is always available to JavaScript. It's what it's designed for. It's designed to be used to JavaScript. And now I'm going to introduce another concept here that's really important in security for Browser Sandbox, is cookies are scoped to a domain, but JavaScript is limited by origin. So browser storage is isolated entirely by origin, and origin is a new concept or a term that is different than domain, and I'll talk about in a slide or two.
Is session storage stored locally on your machine and then deleted when you close the browser? Is it stored somewhere else?
It's inside your browser, but yes, it's on your local machine. And then it gets deleted when your browser closes. So actually, like what you can do is if you browse to the right directory, like in Windows, it's like app data / Chrome temp data / something. You can actually find the files that are in local storage and session storage on your hard drive. Is that what you're asking?
Yes, that's really cool. Thank you.
Yep. Okay. Next, I'm going to talk a little bit about how browsers make HTTP requests, because they make HTTP requests in two distinctly important ways. So first is the OG way, the traditional way that browsers were made back in whenever it was the first browser, like the old Netscape Navigator days before JavaScript was really around. Browsers made HTTP requests. When you typed in a URL in your URL bar and hit enter, the browser kicked off an HTTP request. It handled all the TCP connections and it made the HTTP request for you. Browsers can also kick off HTTP requests via HTTP. So there's lots of tags within HTTP that when the browser is parsing the HTTP, will say, oh, I need to make an HTTP request, and it'll do it automatically. So some happen automatically when a page loads. So things like this, if you put a link style sheet with an href here, this will cause the browser, when it reads this HTTP, to go out and make an HTTP request to fetch hello world. A script with a source will also cause the browser to fetch a JavaScript file over HTTP. Image source, iframe source, all of these happen automatically when the page loads, as the browser is just going down the list of reading HTTP. If it comes across these, boom, the browser sends an HTTP request and fetches that resource. Some of them require an event, like a user clicking. So if there's a tag with a link, this does not automatically get fetched, but as soon as the user clicks on it, the browser will make a request to Google and redirect there. Or if you have a form, for example, with a submit button, when you hit submit, the browser will send a request with the data inside the form. Now, these include cookies automatically. That's where, going back to our same site discussion, this is when the browser makes the determination whether or not to send the cookies based on whatever domain this request is about to go to. If a cookie matches, the browser will send that cookie. And there's not a proper term for these, but I call them HTML requests because they're usually triggered through HTML elements. The other way, more modern way, since JavaScript has kind of become ubiquitous, is the JavaScript way. And JavaScript running inside your browser can also make outbound HTTP requests. And there's two browser APIs that allow for that, XML HTTP request or fetch. JavaScript can make these requests and read the responses silently in the background. So when you load up a page and the JavaScript starts executing, a lot of these requests happen in the background without you being aware because nothing's changing within the DOM. Not necessarily anything's changing within the DOM, but JavaScript in the background is constantly doing it. So like this is a simple example inside a script tag. This is just a for loop and I'm just gonna launch 100 different HTTP requests as soon as the page loads, but I'm doing it from JavaScript. And this is used in AJAX programming or asynchronous JavaScript and XML. It allows you to update the page without having to request a new one. And this is exactly what React and modern single page applications are doing. They're just loading up a bunch of JavaScript and dynamically updating the page via AJAX requests that happen in the background. Okay, now we're going to get to some of the actual security features that are inside a browser that are very important and keep us safe as we browse the web. So thankfully, the designers at Google or Mozilla or Netscape or all the browser developers are smart and understand security. And they recognized early on that if you can just go to any page and that page can load any arbitrary JavaScript and I'm going to execute it, there's some bad security implications that can come from that. So they take a lot of steps to try to protect you as you're browsing the page, browsing the internet and loading and executing arbitrary JavaScript. The two main security boundaries, we talked about one of them is the sandbox. The sandbox dictates that JavaScript should never, ever be able to escape your browser and access your underlying host. So you can't go to a malicious site. That malicious site can't load malicious JavaScript, and that JavaScript can never, ever start reading files on my computer. Or it can't interact with my computer. It's stuck within the browser, and it cannot escape the browser. The other big security boundary is called the same origin policy, or SOP. And this is a sandbox within the sandbox that limits what JavaScript can see and has access to only to within the origin that it was loaded from. So what do I mean by that? Let's call www.example.com an origin. Our browser visits www.example.com. It gets some HTML, it gets some CSS, and it gets a bunch of JavaScript. This is an origin. All of this was loaded from www.example.com, and this JavaScript that was loaded from example.com has full access to the DOM, it has full access to the storage, it has full access to the browser APIs, and it may or may not have access to the cookies. Then let's say I go to chase.com to do some online banking. This is a different origin. The browser kind of spins up a separate sandbox within the browser, and now I have origin B, which is in purple here. And chase.com loads HTML, CSS, and a bunch of JavaScript. Likewise, this JavaScript from Chase can modify the chase.com DOM, it can modify the chase.com storage, it can modify the chase.com cookies or the APIs within the browser, but never ever can JavaScript from chase.com talk to any data from example.com. And never ever can any JavaScript from example.com talk to chase.com. This is a bit of a simplification, but visually this is kind of what happens within your browser. It builds these origin sandboxes and executes JavaScript in them, but the JavaScript within each origin cannot talk cross-origin.
Are separate tabs the same thing as separate windows from a security standpoint, or that's purely a user preference, right?
No, great question. So tabs and windows, we call those browsing contexts. So it doesn't matter if it's a tab or a window, or it could even be an iframe within a page. They all have different browsing contexts, but the context is still limited to the origin. So this is why if I'm on chase.com in one tab and I log in and I get my cookies and I'm looking at my account summary and I open another tab to chase.com, I don't have to log in again. I'm instantly back in my account summary. Those are two browsing contexts, but they're part of the same origin, so they're sharing data. If I have a tab open with chase.com though, and a tab open with example.com, they're different origins. The JavaScript cannot talk or share data between. Does that answer it?
That's great. Thank you.
Mm-hmm.
So what about if you use an API that says, like, that uses stuff from two websites? Does it now have access to like stuff from both websites then?
No, that's what's disallowed basically by the origin sandbox, the same origin policy. I can open up as many tabs as I want to example.com, and all those tabs and browsing contexts will share the same underlying storage and the same underlying cookies. But the JavaScript that comes in from example.com cannot access my storage or my APIs or my cookies from chase.com. So kind of what you can think of is like under the hood, the browser is maintaining this like master list of origins that it's talked to and the data that is associated with those origins. So every cookie, every entry in your local storage database, every DOM is associated with an origin, and it knows exactly what JavaScript came from that origin and allows that JavaScript to access it. But if the JavaScript from chase.com tries to access anything from a different origin, it cannot. And if you were to go, like I mentioned, on your local machine and find the actual data directory where Chrome stores its local storage, they are organized by origin.
Hey, Ronnie, on the are there like technical limitations that prevent it from accessing that, or is it something that's like enforced if somebody discovers that you're accessing someone else's like data?
Yeah, it's very technically limited by the browsers themselves. So it's not even that this JavaScript can't access this, it's that this JavaScript doesn't even know that this exists. The browser like enforces this hard separation. If anyone were to find bypass like within Chrome and prove that they could break out of the origin, it would be a super critical vulnerability that would be patched immediately. But we rely on the browsers to make sure that that cannot happen.
Got it. Thank you.
So maybe this is a bit of a contrived example, but this is why the same origin policy and what the browsers have built is so important. Without this, the web would be a very, very, very dangerous place to be. So without the same origin policy, any site that you visit could load any JavaScript. And that JavaScript, without the same origin policy, would have unfettered access to anything you've ever browsed before. So this is a quick example. I called it an attacker's dream. This doesn't work, but if the same origin policy didn't exist, this would work. Let's say you go to attacker.com or ropnop.com, which is my site. The second you visit my site, I'm going to load some bad JavaScript into your browser. And that JavaScript is going to here execute a function called transfer money. And I'm just going to open a connection to chase.com and transfer me money from your chase.com accounts. And then I'm going to open a connection to Amazon. And because you're already logged into Amazon, I'm going to go ahead and buy a bunch of stuff like on Amazon, like a new MacBook, and ship it to me. This is not allowed by same origin policy because this page, this DOM, and this JavaScript came from attacker.com. The browser will not let this JavaScript interact with chase.com, or it will not let it interact with amazon.com. And all your sensitive chase.com session tokens and JWTs and cache and local storage is inaccessible unless you're actually on chase.com. Does this make sense?
So what if you made a website that had like API access to say Amazon, and through the API you could buy stuff on Amazon. Mm-hmm. If you made a website with that API and got someone to log into your website, could you buy stuff with their Amazon? Or are there other things in place to prevent that?
So not by default. You would have to configure it very specifically to allow that. And that, I think what you're describing is called CORS, or cross-origin resource sharing, which I'll talk about near the end because it gets a lot more technical. But there are ways to allow this to happen, but you have to be very explicit in allowing it to happen. By default, it cannot happen. And in order to allow that to happen, it's actually up to Amazon to allow it to happen. And you would have to coordinate with Amazon and say, I'm building a client-side application and I want it to be able to interact with your APIs, and Amazon will configure something specifically to allow you to do that. But good,
cool. That's
yeah.
Really interesting. Thank you.
Yeah, good question. This is a really contrived example and a high-level overview. But when we get to CORS, remind me, and we'll dig much more into that. It's possible, but it's very technical. But it's also easy to get wrong. Okay, so I've been throwing around the term origins a lot, and origins are different than domains. And depending on what resource we're talking to, origins are much stricter than domains. So let's assume that JavaScript is loaded from https://www.example.com/home/homepage.html. And it wants to access resources at these 5 URLs. Which of these URLs, if any, are considered to be the same origin and would be allowed by the browser? Anyone want to take a guess?
I think maybe A, B, and I think E. Maybe
Okay.
not. E has something weird going on with like the port there and stuff. So maybe just A and B would be my guess.
Okay. Anyone else? So good catch on the port. The answer is actually B only. So for an origin to match, it must match on 3 parts. It must have the exact same scheme, it must have the exact same host, and it must have the exact same port. So A, even though it looks similar, is actually a different domain. It's example.com instead of www.example.com. So therefore A is a different origin, and that's not allowed. B, it matches the scheme, HTTPS, it matches the full domain, and the path doesn't actually matter. So B is allowed. C is HTTP, not HTTPS, so the scheme is different, that's not allowed. This one, api.example.com, is different than www.example.com, that's not allowed. And then this last one, like you called out, different port number, different origin, not allowed.
So what happens when you type in just like google.com into your browser, and then is it redirecting you to the one that's like https://www.google.com?
Yep, usually there's going to be some sort of auto redirect to HTTPS, and then depending on the subdomain, and then like within Google, it gets very complicated very fast, but Google has multiple subdomains and therefore multiple origins, but they have it configured with cores, which I mentioned, so that they can all talk to each other. But by default, none of that would be allowed. Okay. A few more slides, then we'll take a break. But these are great questions, so I don't mind going over here. So how is JavaScript loaded from an origin? Like we talked about this concept, the browser has to remember where JavaScript came from so that it can limit its execution power. Well, how does it know where it came from, right? How is it loaded? Generally, it has to be included somewhere in the HTML that was returned from that server, from that origin. So if I go to example.com and this is the HTML that gets returned from example.com, I'm loading JavaScript in a couple different ways here. I can load JavaScript via a script tag, and this hello.js script is going to be loaded, and this hello.js is therefore considered to be loaded from the origin. I can also, however, load JavaScript from a different server. So this JavaScript here comes from attacker.ropnop. However, because it was initiated from this origin, it's considered to be loaded from this origin. You can also execute JavaScript within HTML attributes. So things like button, on click, equals, and then put draw JavaScript inside here. That JavaScript is considered loaded from this origin. Likewise, you can catch errors, for example, like an image source fail, and then on air execute this JavaScript. That JavaScript executes from this origin. So you can see when this page loads here in my console, I get all these hello messages. All of this JavaScript executed from within the origin because it was loaded within that origin's HTML. Okay, so in summary, before we get into talking about cross-site scripting and OWASP top 10 and those vulnerabilities, everything I just threw at you, all that information is sort of the foundation that we're going to build upon. And understanding web security requires understanding all of these concepts, like knowing the difference between HTTP and HTML and JavaScript, understanding things like the same origin policy and the limits that JavaScript has within those origins. Then all of our security concerns, we can kind of break into 2 categories. I talked about earlier, right? We have you had the traditional front-end dev and the back-end dev. Well, we also have traditional like front-end vulnerabilities and back-end vulnerabilities. So the front-end vulnerabilities are attacks that target the JavaScript that executes in your browser. They're attacks that target the users of your site. Server-side vulnerabilities are attacks that target the site itself. And I'll stress this because in my experience, I have found that it's much easier and more valuable to teach security to web developers than it is to try to teach web development to security professionals. So as developers, because you are practitioners, you are actually already way ahead of a lot of security professionals and pen testers out there and understanding these concepts. So big leg up there. If you want to get into security or you want to just be a very security conscious developer, knowing these concepts and how to build and how web apps work together is a huge plus. So I mentioned the OWASP top 10 a few times, and I'll talk about it now just to see the distinction between those types of vulnerabilities here. The OWASP top 10 is a curated list that comes out every 4 years, and it's sponsored by OWASP, but there's involvement from a lot of big security companies and consulting firms and pen test firms that give data about what they're seeing in the wild as they perform security assessments and penetration tests. And then it's compiled and distilled down into the top 10 web application security risks. And one thing to note is that this is not by any means an exhaustive list. It's just the top 10 most common or riskiest vulns that you should all be aware of, but there's plenty of things that are not on the OWASP top 10 that are out there that, you know, at some point we'll all have to be familiar with.
Why is it only updated every 4 years?
Good question. I think it's a lot of work to put this together, and I don't think things change enough like year to year to actually warrant like an update every year.
So even though like technology is constantly changing, the security risks don't change as fast as the technology does?
Yeah, basically. And the next slide I'll show what those top 10 are. They're categories of vulnerabilities. So it's not like a specific vuln in this new framework of JavaScript. They're categories of vulnerabilities, and for the most part, those categories of vulnerabilities, they may change their form depending on the technology or the language in use, but the overarching like type of vuln or what they're doing doesn't really change. Also, OWASP publishes really good cheat sheets and remediation guidance for each of these vulnerabilities, so it's another great reference and starting point. So these are the OWASP top 10 from 2017. So 2021 that is due to get updated again. Number 1, injection. Number 2, broken authentication. Number 3, sensitive data exposure. Number 4, XML external entities or XXE. Number 5, broken access control. Number 6, security misconfiguration. Number 7, cross-site scripting. Number 8, insecure deserialization. Number 9, using components with known vulnerabilities. And number 10, insufficient logging and monitoring. Now, a couple interesting notes. Basically, since the birth of the OWASP top 10, injection has always been number 1. Never changed. Injection flaws such as SQL injection or LDAP injection or command injection are always the biggest risk to web applications. In 2017, 2 new ones were introduced, XML external entity parsing and deserialization, and that did change because of technology. Basically because of more prevalent use of Java serialization, deserialization vulns became very popular and easily exploitable. And likewise, a lot more XML data being flung around the internet and handled poorly led to much more vulnerabilities in XML parsers. One big thing that dropped out is cross-site request forgery that had been in the top 10 for years, and then in 2017 dropped out of the top 10. Partly, well, not even partly, I would say almost entirely because of the changing technology landscape. CSRF is heavily dependent on cookies, and we're going to do a deep dive on CSRF. CSRF is heavily dependent on cookies, and as more modern applications moved away from cookies and moved more towards JWTs, CSRF became less popular. So broadly speaking of those top 10, you can break them up into 2 categories. I like to think of them as technical vulnerabilities and design vulnerabilities. So technical vulnerabilities occur at the code level. As developers, we're responsible for making sure these technical vulnerabilities never surface. They usually occur when unexpected input is given or handled, and can generally be spotted in code or with scanners. Whereas design vulnerabilities are more like logic flaws. These could be weaknesses in process or the design of the web application. And these are much harder to spot with scanners or automated tools. They require things like threat models or brainstorming or just architecture discussions to try to figure it out. So it's kind of a 50-50 split in the OWASP top 10. Injection, XML, cross-site scripting, and deserialization are all technical vulnerabilities. They're born in code, they exist in code, they can be spotted in code, and they can be fixed in code. Things like broken authentication or sensitive data exposure or insufficient logging, these are like design decisions. These things come up when we're just building the app and how we're designing the app, and we need to be thinking about these types of attacks and vulnerabilities as we're designing and architecting our own application. So I will pause there. This is kind of where I wanted to get to for the first break. Just a quick overview of web application security concepts, and then an intro into the OWASP top 10. But later we will be doing deep dives into cross-site scripting, injection, and cross-site request forgery, which even though it's not in the OWASP top 10 anymore, it's like probably number 11. It's just off the OWASP top 10, and it's still really important to know. So let me pause here, and with all that information, sorry if I overloaded you and just threw this all at you. Any questions or anything that's still not clear you want me to go back on and discuss?
I actually have a quick question, Ronnie.
Mm-hmm.
You mentioned needing permission from these companies before you do this kind of like red team testing. And because some of this information is sensitive, what happens if you still accidentally come across something that you shouldn't have? Like, say you were doing some approved testing and you came across some HIPAA compliant information. How does that go? Do you have to sign an agreement from that point on, or?
Yeah, great question. This is an ongoing debate in the industry, and to our credit, just to our credit in general, the royal we, I suppose, like companies are much more amenable to this type of disclosure now. So what I'm referring to is called responsible disclosure. That's exactly what do you do when you discover a vulnerability and you want to responsibly disclose it? A lot of companies will actually have like security mailers or security contacts that you can find on their site, and they will have their own policy about responsible disclosure, which basically says if you encounter a vulnerability or find a security issue with our code, we would like you to send the information to here, and we'll be in touch, and this is our policy. So it's kind of a murky subject because not every company is going to have a clear process for responsibly disclosing vulnerabilities. In that case, there's actually third parties that exist to help connect you with other responsible parties to handle responsible disclosure. Or you could see if they have a bug bounty program. Like my company, for example, Marqeta, we actually have a responsible disclosure program. It's through BugCrowd, so BugCrowd manages it for us. BugCrowd is a bug bounty company, but you can go to marqeta.com/ I'm gonna blank on the URL. It's something like security disclosure, and there's a whole contact form that you can get in touch with me and my team if you find a vulnerability in Marqeta. And we welcome those, and we thank you for it, and we have a process for dealing with that. If the company you see doesn't have it, sometimes good avenues are to go through their general support, or even reaching out on Twitter and saying, does anyone have a security contact I can get in touch with? It gets trickier when they don't have a well-defined process.
Awesome, thank you.
Mm-hmm. Yeah, I will say the relationship between companies and security researchers has greatly improved in the last couple of years. I'll tell you a quick like horror story. Back when I was at Cisco, Cisco actually had a horrible reputation for dealing with security researchers. There was you can read about this online. I think it was like 2005. A researcher had found some pretty serious vulnerabilities in Cisco gear and was going to speak at Black Hat in Las Vegas. which is a huge security conference. And he had tried to get in touch with Cisco multiple times and say, hey, I found this. And Cisco basically just lawyered up and said, we don't want to hear it. You can't share this. Like, you shouldn't have been doing this in the first place. And then he was about to go on stage at Black Hat, and Cisco filed like some big lawsuits against Black Hat, and it became this whole legal mess where they sued to prevent him from getting on stage and actually talking about these vulnerabilities. And I wasn't at Cisco at the time. This was 15 years ago. And it blew up. It just got such bad publicity. The vulns came out anyway. People saw it. It made Cisco look bad. It made security researchers angry. And to Cisco's credit, they completely turned around and said, we're changing our entire policy. No, like, we're not going to just like lawyer up and sue you if you find a vulnerability. We actually welcome that now. Disclose it to us. We'll work with you. We'll let you talk at Black Hat. We'll let you blog about it. But we just want to know first, and like, here's the steps we can do to work together. So companies are realizing that old model of anyone who finds a security vuln is a hacker and therefore malicious and we're going to sue you is like not the way to go.
Pretty cool that they're wising up.
Yeah. Yep. Yeah, I think hopefully almost every company is now like wisened up, and every big technology company, I mean, the major players like Microsoft and Cisco and Apple, you can find their public websites that are exactly like, here's how we want to welcome vulnerability disclosures, and here's our process, and they'll either pay you via bug bounty, or they'll give you public credit, or they'll give you kudos. Microsoft like publishes a list every year of like their top 10 security researchers. Like they give props to all the people who find vulnerabilities in Microsoft and say thank you publicly.
Ronnie, I have a slightly off-topic question.
Yeah.
Would that be more appropriate to ask like over break?
I mean, you can ask it now. If anyone wants to go on break early, let's see, it's almost 10:40. Maybe we'll take like 15 minutes and come back like 5 before the hour. So I can stay on and you can ask your question now, and we'll pick up at like, well, we can just call it 11. But unfortunately, like, things still happen in our industry. There was a case not too long ago with a couple of consultants from Coalfire who got arrested and thrown in prison like overnight for doing a sanctioned pen test. They were trying to pick locks of a company, and even though they had permission, they didn't have permission from the right person, and the cop didn't understand it, and they still got in a whole mess of legal trouble. And Coalfire was a big enough company with a big enough legal team to help them out and get it covered. But yeah, there's risks when you're doing it like that. All right, well, it's 11. Let's jump back into the slides and talk about some security testing and cross-site scripting. We'll see how far we get. I do want to make sure I give everyone like a lunch break. So we'll go for like an hour or a little over an hour, and then take a break there for the afternoon. Okay, so in this section, I'm going to talk about the tools of the trade a little bit, and how attackers and testers are actually looking for vulnerabilities, specifically web application like layer 7 vulnerabilities. So one important thing to remember when it comes to like testing web applications or APIs is it's all just HTTP. And modern web apps can seem really complicated, and whether you're using React or some equivalent client-side framework that has so much magic behind it, and like it just gets really convoluted and crazy with the amount of JavaScript, at the end of the day, every web application has to talk to a server over HTTP. It's just a client, aka a browser, talking to a server over HTTP, which is the protocol. So even if your entire client-side application is written in JavaScript, that JavaScript is going to send HTTP to the server. And so when we are testing web applications to try to find vulnerabilities, it's always just a matter of reading, sending, and modifying HTTP traffic. That's almost entirely what we're just looking at. We're just looking at the HTTP traffic that's going to be coming from the client to the server. So when we're manually testing these web apps, it's all about sending custom HTTP. How can we do that? Well, HTTP is just a plain text protocol. Like you saw in that one screenshot earlier, if I wanted to, I could just open up a TCP connection to a server and start writing data to it. But a much better way is to use a proxy. So a proxy, and this logo here is the Burp Suite proxy. So we'll be using Burp Suite in the labs, and I'll talk about Burp Suite. But a proxy is a great way to actually be able to see and understand what's going on under the hood of a web application by reading the HTTP request that it's sending. So if we go back, like our traditional web app, Firefox here, when we browse to our site, it's going to kick off a GET request for like the index.html page. The server is going to send it. That HTML page is probably going to load some or request some JavaScript. So then we're going to request the JavaScript, and the JavaScript's going to come back, and then we're going to execute the JavaScript, and that JavaScript might request things like images or other things, and all of that's happening, automatically between the client and the server. When we have a proxy, what we need to do is inject that proxy in between that communication path. So the browser is going to send its request to the server, but the proxy, it's going to have to go through Burp Suite or the proxy. And the server's responses are going to go back to the client, but they're going to have to go back through the proxy. So Burp Suite and OWASP Zap are two security-focused web proxies. There's a lot of other web proxies out there. There's proxies that specialize in like helping developers debug or POC code, but Burp Suite and Zap are purpose-built for security testing. So they have a lot of really cool features built in that help with security testing. And proxies will let us view, pause, and modify HTTP traffic in transit. And the majority of web app attacks, like the majority of those technical vulns that I talked about in the OWASP top 10, are really just all about sending unexpected HTTP requests to a server, and the server doesn't know how to handle them, and then it doesn't handle them appropriately or doesn't handle them safely. So with a proxy in the middle intercepting here, we can browse to an application, and that application, we're taking the quote unquote happy path. We're doing what we're supposed to be doing in that application, and it's going to send a quote unquote good request. Well, when we're in this proxy, what we can do is we can take that good request and we can make it bad. And then we're going to forward that bad request on to the server. And if the server is vulnerable or misconfigured some way, it may not know how to handle this bad request, and it might send a WTF response. That's not a technical term. That's just what I'm calling it, which is the server just doesn't know how to respond to this. And then that WTF response will get passed back to the client. These WTF responses are what we as security testers live for. We want to trigger these WTF responses. It's all about finding these WTF responses and finding them if they're vulnerable and then exploiting them. Now, the one thing to note about injecting a client or a proxy here is that for the most part, this proxy is invisible. Our client, whether it's Firefox or Chrome, thinks that it's talking to the server, and the server thinks that it's talking back to the client. So this is kind of an invisible layer here, but really both of them are talking to our proxy. And that's how we're able to modify these requests and pass them back. Like the server actually thinks that it's receiving requests directly from the client, and the client thinks it's receiving responses directly from the server, but they're both talking to this man-in-the-middle proxy. Now you might be asking yourself, well, what about encryption? So SSL, TLS, if we're talking over HTTPS, I mean, this is almost exactly what HTTPS is designed to prevent. HTTPS is supposed to be encrypted end-to-end with proof of identity between the server and the client. And you shouldn't be ever allowed to actually look at traffic that gets sent from, say, Firefox or Chrome to google.com servers. And that's true. Properly configured SSL TLS prevents man-in-the-middle attacks, which is what we're doing here. The data is encrypted, it's garbled, we cannot read it, we cannot modify it, and the browser knows that it's talking to google.com because google.com's certificate is trusted, and that entire communication chain is encrypted. Except we are doing this to ourselves. So we are always going to be able to break our own security, break our own encryption for the purposes of testing. Now we're doing this to ourselves. We are not doing this to anyone else. Since we control our client, we can also control the SSL configuration. So what happens with SSL or TLS with an intercepting proxy like Burp is Burp Suite will actually handle the SSL termination and re-encryption for us automatically. So visually what that looks like is if I'm on my client and I type in google.com, it's going to go to the proxy, and the proxy is going to return an HTTPS certificate. The client is going to encrypt the data to the proxy. So between the browser and the proxy, it's HTTPS encrypted. And then the tool like Burp Suite is going to immediately decrypt that traffic for us, let us see it, let us modify it if we want, and then when it goes to send it on, it's going to re-encrypt it with the server certificate. So it's encrypted here, but it's actually unencrypted inside the proxy for us to view it. And we have to configure that ourselves and deliberately force this kind of TLS misconfiguration, but we're doing that to aid us with security testing. So important to remember, right, that we can't do this to someone else's. If you are looking in Burp and you see like plain text passwords or plain text credit card information or something like that, it's not bad because it's only yours. You can only do it to yourself. You can't do this to someone else. Which brings me to the golden rule of web security, as we talked about those WTF responses. The golden rule of web security as you're building a server is never, ever, under any circumstance, not even for a second, ever even consider trusting user input. You cannot ever trust that what is being sent to you is what you expect to be sent. It's too easy for attackers to use tools like proxies and to send those bad requests that you can never be stuck assuming that what you're receiving is good and can be trusted. So web applications have to be designed to handle the unexpected. That happy path cannot ever be assumed because you know what happens when you assume. And you'll be very unhappy when that happy path is not taken. So if you take one thing away from this whole web security workshop, just take my golden rule and just don't ever, ever, ever trust any data that you're getting. You have to design your application and treat all data as if it's untrusted. Okay, before I jump into the technical deep dives on cross-site scripting, any questions on proxies? Have any of you like used an intercepting proxy before or looked at HTTP traffic under the hood like that? When we get this set up, and if you download and install Burp Suite, it's also super helpful, not even from a security perspective, but I use Burp Suite all the time just to help debug my own web servers and my own web applications. Sometimes I'm getting random errors and I just actually need to see what's being sent. And as soon as I can see what's being sent inside the proxy, it's like, oh, duh, I forgot to escape that, or like I should have put a semicolon there or something like that. So they're not just useful for security, they're also really useful if you're debugging or testing your own server.
I have a question, Ronnie.
Yep.
Could you go back to that last slide real quick? Yeah, so is that kind of similar to like doing like port forwarding with something that would be available? So are we able to look at this traffic because we're sitting between the client and the web server? And is that what you meant by proxy like that for Burp Suite?
Yep. Yeah. So you can call it like man in the middle, but basically we just have to. What we're trying to do with our proxy is get the traffic to hit us, and you can do that through like a couple different ways. For web traffic, it's pretty easy because browsers have the option or the ability to configure proxies, and there's plenty of valid use cases for proxies. Like not using a proxy is not bad. Don't equate that with like an evil person trying to intercept traffic. So we can configure Firefox or Chrome or whatever browser we're using and just tell it that, hey, all the traffic that you send, the first hop has to be this proxy. And they'll gladly do that for us. Now, there's more malicious ways of doing that. And this might be what you were getting at, like if you hear attackers or like, nation state actors hijacking network routes or doing things like ARP spoofing or DNS
I think that's what I
hijacking.
was thinking of.
Yeah, like DNS
Yeah, like
hijacking or BGP hijacking. There's attacks that you can do at the network layer to force traffic to come to you.
Okay, yeah, force it to come to you, and then you would forward it after it comes to you, and either you tamper or eavesdrop, and then you forward it to its legitimate destination.
Exactly, yeah. So that's like the forced way of doing it, like the I don't know, the malicious way maybe of doing it. And yeah, in our case, like we're doing this, we're testing our own app, we're testing our own traffic, so we don't need to like maliciously force it. We can actually just tell Firefox, like, just send your data to this proxy for us, and it will. But yeah, if you wanted to do it like a grand scale, I mean, you hear stories of like nation state hackers or like the Russian groups hijacking entire BGP routes. So like all traffic destined for one country hits one of their servers first before it goes to that country. I mean, you can do this like at grand scales and just get massive amounts of traffic. But we're doing it very, very microscopically, like just this browser and just this server.
That's cool. Thank you.
Mm-hmm. I saw a chat thing pop up, but I can't see.
Don't worry about it. That
Okay.
was just me. That was just me explaining a little more detail about how we set up burp to the browser to route the request and the response.
Yep. Yeah. And so we'll do that after lunch too. Everyone will download burp, and it makes it super easy to get this set up and configured. All right, so now I'm going to dive into the first of the 3 vulns that I want to talk about, and this is the deeper dive into conceptually how these vulnerabilities exist and why they work and why they're bad. So the first one is cross-site scripting. Has everyone heard of cross-site scripting? It's like a pretty common term, but it can be a confusing vulnerability. I'll leave it that way. So cross-site scripting, which is abbreviated XSS because CSS was already taken. So XSS or cross-site scripting, this is my definition. It occurs when an attacker is able to force a victim's browser to execute JavaScript within a trusted origin. My gripe with cross-site scripting is that it's a terrible name. I think the name causes a lot of confusion. So my recommendation would be kind of ignore the name. Don't think about the cross-site part because it's actually all about loading and executing JavaScript within the same site or the origin. Now we talked about the same origin policy. Cross-site scripting basically allows an attacker to bypass that same origin policy by getting their malicious JavaScript to run in the same origin as the site they wish to target. And this is accomplished through content injection. And content injection might actually be a better term for cross-site scripting than cross-site scripting itself. So this is really about content injection, in which malicious JavaScript is injected in a valid HTTP response from the origin. So hopefully this is all going to make sense in a slide or two. It's more easy to visually represent this than just talk about it. So review, we know that same origin policy disallows an attacker's script from interacting cross-origin. That's one of the fundamental security boundaries of web applications and browsers, right? Is if I am my evil attacker over here on my origin B, whatever JavaScript I want to execute or host, I'm limited by the same origin policy. I can't actually read or interact with anything from chase.com. So you can visit my attacker site and I can give you my malicious JavaScript, but the browser is going to prevent my malicious JavaScript from talking to chase.com or reading your chase.com sensitive data and storage or rendering your chase.com DOM. That's what same origin policy prevents. However, in a cross-site scripting attack, this malicious JavaScript here gets smuggled inside a legitimate HTTP response so that it gets executed inside the origin. So this is kind of what it looks like conceptually. I have my attacker. This is my malicious JavaScript to steal your chase.com credentials. As we know, I can't just do that directly. Same origin policy prevents this. So instead, if I find a vulnerability in chase.com, I can send my malicious JavaScript to the chase.com server, and the chase.com server will reflect or send my JavaScript back into the actual chase.com DOM. Now my malicious JavaScript has ended up inside this security barrier of this chase.com origin. The reason being because to the browser, the JavaScript came from the chase.com server, therefore it's trusted, therefore it gets executed with all the permissions of everything else within chase.com. You with me still conceptually? Visually, this is what a cross-site scripting attack does. It's about smuggling bad JavaScript from origin B into origin A.
So the servers, for some reason, thought that, quote, dirty code was clean code and sent it anyway?
Yep. So this is a vulnerability in chase.com. Like you can't just do this out of the box, right? But there's the cross-site scripting vulnerability is what allows this step in the middle here to happen. And yeah, it's usually because the browser interprets this as good when it's bad and includes it with the other good stuff. So there's 3 techniques to doing cross-site scripting or content injection. And they all end up in the same goal, which is our JavaScript is executing in the chase.com origin. But they accomplish it slightly different. So the first is what we call reflected cross-site scripting. And in a reflected cross-site scripting attack, an attacker is able to load JavaScript from a trusted origin by reflecting it up to and back from the server. And this is usually done through some sort of social engineering. So I have to send like a malicious link or a payload to somebody and have them click on it. So what this looks like is I will send a link to my victim over here and say, hey, click this link. And it'll be a chase.com server with this red cross-site scripting payload here. You can think of this as actually like all the JavaScript and everything bad I want to execute. Somehow part of that link. It'll be part of the URL. The user is going to click on that link and it's going to submit a HTTP request to the chase.com server with that malicious JavaScript embedded inside the URL. The server responds with content, but that content includes what was sent. That's the reflecting part. It's gonna the content coming back from the server reflects what was sent to it. Now, because this cross-site scripting came from chase.com, it's going to execute within the chase.com origin. It's considered trusted, and now we have malicious code execution inside the chase.com origin on the victim's browser. So the reflecting part here is what's important, because this is what tricks the browser into thinking that this malicious JavaScript is trusted because it actually did come from chase.com. Even though I kind of had to do one extra step of getting you to click a link, but I had to do that round robin for it to come back into the browser. The other approach is called stored cross-site scripting or persistent cross-site scripting. In this one, the difference is the attacker is able to load the JavaScript from a trusted origin by storing it on the server, and then it's returned in the responses. And this is usually done by storing a cross-site scripting payload in some sort of persistent field. And by that, I mean something like a comment on a blog post or something that I can enter and then the server saves it and other people can see it. And this is very dangerous because this affects any user who visits the correct page and not just the user that I'm targeting. So visually it looks like this. I'm going to send my same bad JavaScript cross-site scripting payload to some endpoint on a chase.com server. And the chase.com server is going to save that in a database. So you can imagine like I guess Chase doesn't really probably have like blog posts that you can comment on, but think about like I submit a comment on a blog post, the server saves my comment in a database. Then the victim, when they go to that URL, the server retrieves the data from the database and then sends it back to the victim. Well, now this malicious JavaScript has come from the chase.com origin. It's executed and it's running, and we have cross-site scripting. There's a famous or infamous case of persistent cross-site scripting that I will send a link out in Slack, or someone could probably find it, called the Sammy worm in MySpace. And I don't know if any of you have heard of this before, but this is back when like MySpace was getting very popular. This security researcher named Sammy Kamkar found a persistent cross-site scripting vulnerability on MySpace. He could put something on his MySpace profile with that stored malicious JavaScript. And then anyone who visited his profile would load this malicious JavaScript from MySpace, and it would execute inside the MySpace origin. Now, he wasn't really like a bad guy, so he just made this JavaScript add him as a friend. It forced you to add him as a friend on MySpace. And then it propagated itself, and it wrote the same cross-site scripting payload to your profile, and then sent it out to all your friends. So he basically made a worm out of cross-site scripting on MySpace. And I think he unleashed this on his profile, and within 24 hours, he had the most friends of anyone on MySpace, and he caused all of MySpace servers to crash because they weren't prepared for having one person have that many friends. So this was a classic example of a stored cross-site scripting on MySpace that he was able to do, and it really wasn't that malicious. It just added him as a friend, but it propagated itself, and it totally got out of control within like 24 hours. The third technique for content injection for cross-site scripting is called DOM-based cross-site scripting. This is a lot harder to visualize, but unfortunately, it's a lot more prevalent now because it abuses client-side applications and frameworks like React or Angular. The difference between DOM-based cross-site scripting and the others is that the server isn't actually really involved in this. It's a vulnerability that exists within the client-side application, so within your React app or within your Angular app or whatever framework you're using. And in this, you're able to load JavaScript from a trusted origin by passing it into already trusted JavaScript. What I mean by that is if I go to chase.com and they load up a client-side application, it's like a big fat app.js file, all that JavaScript is already trusted and it's already running. If I can send data that gets injected into that already running JavaScript and hijack execution control, then I've basically got cross-site scripting by, I can inject my malicious JavaScript into already trusted code. So this client-side app in green is already trusted, it's already executing, it already has full access to the origin. There's certain situations where you can send in malicious payloads as part of like JavaScript variables. And if the client-side app is misconfigured and executes what's inside the variable content, you can hijack execution flow and take control of the already trusted app.js. That's a simplified explanation, but conceptually, does that one kind of make sense? Cool. So what can you do with cross-site scripting? So pen testers love to use alert1 as their cross-site scripting payloads, but in reality, that really doesn't demonstrate any severity. If you see an alert box that says 1, all this means is that I've been able to execute any JavaScript that I want. But an alert box is a very visual way to show that you can execute JavaScript without actually causing any damage. So that's why this is a really popular proof of concept. Seeing someone pop an alert box that says 1, it's a really short JavaScript payload, but what it represents is quite scary. So by the way, I did not find a cross-site scripting payload on chase.com. This is contrived. I built this out. But this is what a cross-site scripting attack could look like on chase.com. If I got chase.com to pop an alert box, that could demonstrate a pretty severe cross-site scripting vulnerability. But what can you do? So if you have alert 1, it means you really have any JavaScript you want. And when this happens, same origin policy no longer applies. So basically, the foundation of web security is gone. That JavaScript can control everything on the page. So if I control the JavaScript, I control everything. If you're on chase.com and I get malicious JavaScript execution, I can totally make chase.com look however I want by controlling the DOM. I can read and write any sensitive information that you might have in your session storage, like your JWTs. I might be able to read or write or use your cookies, or I could interact with like APIs that chase.com has permission to. So you can read sensitive data, you can make requests, you can modify the DOM. You really have complete control over the origin. And I kind of like to think of it as when in a cross-site scripting attack, you're infected. You've been infected with bad JavaScript, and anything within that origin can no longer be trusted. So in summary, cross-site scripting is just content injection. We're talking about injecting JavaScript into a site. And then when that happens, since that malicious JavaScript comes from the origin, the browser trusts it. And then the same origin policy does not apply because it's all within the same origin. So since JavaScript is all powerful and can control the DOM and the storage and the requests, if an attacker takes control of it, you can't trust anything within that origin anymore on that browser. So it's basically full read-write access within an origin. It's a bypass of the same origin policy by getting inside the origin and then taking complete control of it.
Maybe you answered this, but I didn't catch it. Does this apply to only a specific? This only applies to a specific user, right? Because a user has to have clicked on the link, and so it's not like this wouldn't be integrated then with like Chase's underlying code, right?
Yeah. Yep.
And then start impacting all its users. So like if an attacker especially wants to do this to like a very wealthy person so that they can transfer that person's money to themselves versus like me, where it wouldn't actually do them that much good.
Yeah, so cross-site scripting is a client-side vulnerability. So that means that we're always targeting the end user. We're not taking control of Chase.com's backend servers. We're not taking control of their money, right? We're taking control of a user's browser when we exploit this. But depending on the type of cross-site scripting attack that you're using, you're either targeting like one individual or a select group of individuals, which would be like reflected cross-site scripting. When you send something to a user, like I'm deliberately targeting this person or this group of people to click this link to get my JavaScript to execute. For stored, this is where it gets a bit more dangerous because I might store my cross-site scripting payload, and then if this was like on the main page of chase.com, anybody who visits the main page of chase.com will get infected. And this was the case of like what happened in the MySpace worm, is anyone who visited Sammy's profile page got infected, but then they infected their own profile page. So then anyone that visited their profile page and anyone who visited theirs, and that's how it spread like a pyramid. So
got it. Thank you. Yeah, you of course you talked about all of this, and I just didn't put it.
No, it's good. No, it's a really good question, and it's good to clarify that. Yeah, we're usually talking about targeting individual end users with cross-site scripting, but there's also cases where you can target or infect every user of a website. Yeah, good question. Any other questions on just high-level cross-site scripting summary? Because I'm going to jump in next to a different vulnerability. Oh, I guess I'm actually not. I'm going to talk about mitigating it first. Thought my next slide, thought that was it. So yeah, how could I forget? I actually need to show you how to prevent this, right? So how do you prevent or mitigate cross-site scripting? Well, it's all about injecting content into the DOM, which the browser interprets. So as everything, it circles back to the golden rule of security. Never trust untrusted data, never insert untrusted data into the DOM directly. So if I'm chase.com, any request that I'm getting, I have to treat as untrusted. Any data that comes in from that request, I have to treat as untrusted, and I should never just blindly push it back in a reflected response, right? Never inject it back into my HTML because that could contain nasty JavaScript characters or nasty payloads, right? So there's a couple ways to do that. One would be input validation. In input validation, what we do is it's kind of like a whitelist. We just reject anything that's unexpected. If I have a form that expects you to enter a zip code and you send me like 300 characters of JavaScript, that's not a zip code. I can just pretty much block that immediately. Like I know I'm only looking for like 5 digits. That's validation. The other way is sanitization, which would just be remove any special characters. It's not possible to get JavaScript execution without the use of certain special characters. And those special characters are the characters that actually mean something to HTML parsers. So things like open brackets, quotes, colons, things that are not just alphanumeric. So what we could do is anytime we get data from a user, we can just strip out every special character. Only keep the letters and numbers. That's one way to do it. The other way, though, is because sometimes maybe those special characters are actually needed. Punctuation marks, for example, is we can encode them. If you can escape or encode all the special characters in the HTML response, you are safe from cross-site scripting. So going all the way back to what we talked about with URL and HTML encoding, if you take every bracket, every exclamation point, every pound sign, every colon and semicolon, and instead of just treating them like raw characters, you encode them, the browser will not interpret them as actual valid characters, and you will not get cross-site scripting. So you can do that both on the server side or on the client side. Since you're using, most of you, I think you're using Django. Django does this automatically for you, which is great. This is why using frameworks is awesome. You get a lot of security features out of the box. The built-in escape function in Django does that automatic conversion for us. Here's the brackets that get converted to, here's the quotes that get converted. Here's the ampersand that gets converted. You don't even need to think about it as long as you're actually using the defaults in Django. On the client side, you never want to write untrusted content into the DOM directly. So in JavaScript, there's the ability to write raw HTML with inner HTML. That's a mistake. You should always use inner text because that tells JavaScript to only read, like basically only display the text and not try to parse it as HTML. There's also a great framework called DOM Purify, which is a JavaScript library that you can just call anytime you're about to handle untrusted input, and it will do all of the same encoding and escaping that like Django would do, but do it on the client side. Or lastly, client-side frameworks also do this by default. Security by default is great. For example, in React, if you're using data binding within your components, React will automatically do escaping for you. So here's a dead simple, right, React function to return my component with a data binding for my data. This variable interpolation here, React will automatically treat as untrusted and do the escaping and the encoding for you. Now within React, you can turn that off, but I believe the function call to turn that off is called something like dangerously set HTML or like dangerously decode. Like it has the word danger in it, which is great on the React developers' parts to remind you like this is dangerous what you're doing. You probably need to think twice about it. Now I'll ask, because that's the end of cross-site scripting. I forgot about the mitigation. Does this make sense? Have any of you come across this before, or if you're using Django and React by default, you're probably pretty protected already without even knowing it? I would love to see a world where cross-site scripting goes away. I think we're getting there as more of these frameworks just have secure by default decisions. Like React, it can be hard to actually introduce cross-site scripting into React if you're only using like the default data bindings. That's great. Same with server side, right? This was so much more prevalent when PHP was being used everywhere, which didn't have any of these protections by default. The problems just still always arise anytime you're doing like something custom or leaving the framework to implement something on your own. Be careful. That's all you can really say. And then follow the golden rule. Any data you're getting from the client has to go through DOM Purify. It has to be escaped. It has to be handled safely because you can never ever trust it. Cool. Then we're going to switch gears now and talk about cross-site request forgery. And this harkens back to the discussion we had earlier this morning about cookies and same site. And so hopefully we'll see now like why cookies are kind of a security nightmare and how same site addresses those. So CSRF can kind of be thought of as another bypass of the same origin policy. It's another way for an attacker to bypass the built-in browser security control that is same origin policy. So according to same origin policy, we know that resources loaded from one origin should not be able to write data to another origin. So if I have my attacker origin and my malicious JavaScript, I can't write data to chase.com. And by write data, I mean like send a post request or tell chase.com to initiate a transfer. That's disallowed. Same origin policy at the browser will say, hold on, something's coming from attacker.com and trying to talk to chase.com, and the JavaScript is trying to do that. Like, that's not allowed. I'm going to drop that. And that's basically what same origin policy in your browser would do. However, there's two big exceptions to the same origin policy in this regard. One, same origin policy really only applies to JavaScript. So HTML requests are kind of exempt from this. The second is cookies. Cookies don't have to do with JavaScript, and cookies get sent automatically with requests. So CSRF abuses these two exceptions to basically write cross-origin. HTML from origin B can actually send requests to origin A, and any request from origin B, or any request from anywhere that's going to origin A, if the browser has a cookie that matches origin A, it gets sent automatically. And that is CSRF. So two things about CSRF. It requires a few things. It's a bit of a special vuln that needs a few things to happen in order to actually be exploitable. First is it requires a state-changing request, what I've been calling a write, W-R-I-T-E. And this means that it needs to, the request that we send needs to do something. It has to take an action. It has to initiate a transfer. It has to change a password. It has to post something. Read-only requests don't really get affected by CSRF. You can't do anything with those. Also, your application or your server needs to use cookie-based authentication. No cookies equals no CSRF. This is specifically a vulnerability around using cookies. And it's always going to require some sort of user interaction. Similar to the cross-site scripting example we talked about, you're going to target an individual user. This isn't a mass vulnerability against a server. We're finding or targeting individual users of that server. And it abuses the fact that HTTP is stateless. Servers cannot distinguish legitimate requests from illegitimate requests. Every request to a server is standalone, and the server has to parse them. It also abuses that cookies are automatically sent. This is bad behavior, but it's been around forever since cookies were invented. And then it also abuses the fact that HTML requests are not subject to the same origin policy. So you cannot use JavaScript or AJAX for cross-site request forgery. Okay, hopefully this will clarify a little bit what it looks like. So visually, this is what it looks like. We're again targeting a user on chase.com. I send a link to a user, and the link takes them to my attacker website. So attacker.com/csurf. And at /csurf, I'm hosting a special csurf payload. And the csurf payload is just HTML. It's just a malicious HTML page. So the victim clicks on the link and talks with attacker.com. Attacker.com sends back malicious HTML. Notice this is malicious HTML, not malicious JavaScript like the cross-site scripting example. We're targeting HTML here. So malicious HTML comes back into the victim's browser. This malicious HTML has a post request form to chase.com and a post request to like /account transfer to send money, right? Some sort of state changing request is embedded inside this HTML. The browser sends that post request automatically. Because it's HTML, it doesn't do any same origin policy checks. And because the victim already has cookies associated with chase.com, cookies get automatically sent with that post request. So now we've tricked the victim into sending a transfer post request to chase.com, authenticated with cookies, even though they didn't initiate that because it came in from this malicious HTML right here. The server has no way of distinguishing whether or not this like request to transfer money is legitimate or not. Because the server, it's just not possible with the stateless nature of HTTP. The server doesn't remember like who it's talking to or whether or not they asked for the transfer. It just got a request to transfer money. The request came in with valid cookies. It goes ahead and it transfers the money. So csurf is pretty easy to exploit. It doesn't take much, right? This entire thing here, 6 lines of HTML, is all it takes to actually exploit csurf. And all it takes is just HTML that is going to send a post request to a different site with all the values that we want. So this is very contrived. This is not actually how you transfer money with chase.com, but just, imagine it's something like this. A post request to /account/transfer with the value of who you want to send the money to and the amount you want to send. I embed this malicious HTML on my site. And then these 2 lines of JavaScript here, all these do is just automatically send the form when the page is loaded. So you don't even need to have the user click on submit. You can just submit it for them. But this post request, when it goes out from the browser, will go to the browser will see that you're making a request to chase.com, and the browser will look up to see if you have any cookies for chase.com. And if you do have any cookies for chase.com, the browser sends them automatically. And that's how you are able to exploit csurf, by sending valid cookies or valid authentication material. So this is what it looks like in a proxy. Like I did this to myself. I clicked on that link, even though it was coming from attacker.com. I sent the values that I needed, like send $1,000 to Ropnop, and all of these cookie values were just automatically added to my request when it was going outbound, because the browser thinks that thinks that I want to send my cookies to chase.com. Now, I don't remember who was asking me earlier about same-site cookies, but this is a great example of what same-site cookies can prevent. One thing to notice, and I didn't call this out, but this request is going to chase.com. So you can read the HTTP request. The host is the destination, www.chase.com. There's a header called origin, and origin means where this post is coming from. It means that my client was on this page when I initiated this request. So localhost, because I was just serving up this POC to myself, I'm actually coming from localhost and going to chase.com. All of these cookies were automatically sent. Now, if these cookies had the same site flag set to strict, the browser would compare the origin and the destination. And if the origin and the destination are not the same, none of the cookies would be sent. But chase.com does not have same site set on these cookies. So even though the origin and the destination are different, the cookies get sent. So how do we prevent CSRF? Again, going back to just not trusting user input. In this case, the user is authenticated and we still can't trust them because we don't know whether or not those cookies were sent legitimately or if they were sent via a cross-site request forgery account. So there's a couple traditional defenses to CSRF. The main one is called synchronizer tokens or CSRF tokens. And what this does is it tries to correlate any incoming request with a previous outgoing response. So if the server is going to send us a form to say transfer money, what it'll do is it'll actually append a random value to that form. And then when the form is submitted, the server checks to make sure that that random value is there. If it is, then the server knows that that form is being submitted as a result of a form that was already sent. So you can't you can't skip the receive the form before you send the form. And make sure that you received the form before you sent the form by using this random value. And Django and server-side frameworks can do this automatically for you. But the cooler approach, maybe the more modern approach, is to leverage the same origin policy in our favor. And since we know that the same origin policy only applies to JavaScript, all we need to do is not do this over HTML and do this over JavaScript instead. And there's two approaches to do that. We can either do it through what are called double submit cookies, in which a random value is submitted in both a cookie and the body of the request. And I'm going to show these visually in a minute. Or through custom headers. Or the third approach, which it sounds like you're doing with JWTs, which is great, is just don't use cookies at all. If you want to eliminate cross-site request forgery and you're designing an application from the ground up and you can get away with just not using cookies at all, then you don't have to worry or think about this at all. So I want to show kind of how you would implement some CSRF protections here. Our previous vulnerable example was just a form that was pure HTML. In this case, we're actually going to use JavaScript to send the form. So we have our traditional HTML form, but we hijack the onClick event to execute a JavaScript function called submit form. When submit form gets executed, JavaScript is actually the one that's going to handle the logic here. And what it's going to do is it's going to read in this case, what it's going to do is actually read your cookies. And it's going to see if you have a cookie called CSRF token. Then the value of CSRF token is going to be appended into the form data, and then the form is going to be submitted. So why does this work? It's because JavaScript can only read cookies if it's already executing inside the trusted origin. So if this HTML, if this JavaScript was executing on attacker.com, this get cookie state, right, or get cookie function right here would just fail because it cannot read chase.com's cookies because it's loading, it was loaded from and is executing in attacker.com. So because of the same origin policy, the only way this submission can ever be successful is if the submission is initiated and coming already inside the origin. And that's how same origin policy can defeat CSRF. And most modern side client-side frameworks can actually do this automatically. And I don't know about React, but Angular, if you have a special cookie called xsurf-token, Angular will automatically append that cookie in all outgoing requests without you thinking about it. So again, using kind of secure by default frameworks helps a lot here. On the server side, the check is really easy. As long as you have a cookie value that matches a value inside the body, you can trust this request. If these do not match, you have to reject it. Perhaps a simpler approach, and again, using JavaScript to defeat this, is we can just also add in a custom header. It is impossible to send custom headers with pure HTML. You have to use JavaScript to send a custom header. So again, if we take our HTML form and instead submit it with JavaScript, and we do this xhr.setRequestHeader, and it doesn't even matter really what the value is, but we can call it xsurf or something, and then send it, all the server has to do is validate that this custom header exists. And then the server can know that, okay, JavaScript sent this request because it has a custom header. The only way JavaScript would be able to send this request with a custom header is if it was already inside my trusted origin. So therefore I can trust this and I will allow it. If that custom header does not exist, then you should not trust that this request came from the origin and therefore deny it. So in summary, cross-site request forgery is an interesting vulnerability that abuses what I call, or I consider like legacy functionality of cookies and browsers. It abuses legacy HTML and cookie behavior to basically just not even invoke the same origin policy. But it requires, it's only exploitable in certain circumstances, right? Cookie-based authentication has to be used, and you have to do it in pure HTML. You cannot use JavaScript. But it allows an attacker to write data cross-origin without invoking this SOP. So whereas cross-site scripting, I think I said in the summary, is like full read and write access, cross-site request forgery is kind of a blind vulnerability. All you can do is write data, but you can't actually like do anything after that. So you're just blindly writing or changing server-side state. But it's pretty easy to prevent. And you can prevent it by just using JavaScript, because then the same origin policy kicks in. Or like I mentioned, just don't use cookies at all. All right, that was a ton of data thrown at you there on cross-site request forgery. That is a tricky vulnerability to understand, like why it works and how to prevent it. It's probably in like trainings I've given and just talking with like security engineers, like one of the more difficult ones to understand conceptually. So I want to pause there and open it up if there's like any questions, or if that did not make sense at all, let me know.